In the previous video, we established that we need machine learning explainability to gain insight into our models, to detect bias, debug issues, comply with regulatory requirements, and ultimately trust that our models are safe for deployment in high-stakes decisions. In this video, we will review some options to do so. We could use interpretable models such as decision trees. The decision path of the question, is this a penguin, can be answered by traversing from top to bottom. Has feathers, true, can fly, false, then it must be a penguin. To get an explanation, all we have to do is trace down the path of the decision tree. In other words, the structure of the model is the explanation. Before we examine additional explainability options, it is important that we establish some key terms. Interpretable models, such as decision trees, are referred to as white box models. This is referring to their inner logic being understood. And typically, as we have just seen, the structure of the model is the explanation. By contrast, black box models accomplish their task without us understanding why they arrived at a particular decision. Although in some cases the logic can be intentionally hidden to protect some type of intellectual property, for instance, models can be considered black boxes due to their complexity. If we can use a white box model to get the job done, we should. In this widely cited paper by Cynthia Rudin, she argues that there is widespread use of black box models for many problems where a simpler white box model will get the job done just as effectively. She is right. The key idea here is that we should not give up on white box models like decision trees or logistic regression, because for many problems, they get the job done and we can understand them. One limitation of interpretable models is that once they grow beyond a certain size, tracing down a decision path becomes difficult. Imagine a doctor communicating to a patient the reason for needing to go on a course of medications is some combination of 50 factors that contributed to a decision. Clearly, a long explanation is not useful to an average user. We have a cognitive budget that we can't exceed, and for many problems, we need our models to grow to take advantage of a large number of features and a higher order of complexity. To illustrate how large machine learning models can get, here is a reference to a model with 175 billion parameters to solve a natural language processing problem. Complexity for models with a large number of features is inevitable. This means, while we do want to avoid complex black box models if we can, there are complex problems that do require complex solutions. One option for explainability is to use models like random forest that have built-in capability to provide a global explanation. A global explanation in this case is provided as the top features that the model relied on to make a prediction. In this example, we are seeing the global features that the random forest model used to predict the chances of survival for a Titanic passenger. You can see that the top predictors of the chances of survival are gender, followed by age, fear, and so forth. It is not a full explanation, but it is directionally helpful in understanding the logic of the model. The explanation is global because it is provided for the entire population. The explanation is also model-specific because it is a feature of random forests. Global model explanations may not be useful in some cases. For example, smoking and high cholesterol are two of the top predictors for developing heart disease. If these two conditions don't apply to a specific patient, the explanation will not change. Alternatively, local explanations provide insight into what contributed to the decision for a specific instance. Local explanations can be useful in managing complexity because there is less of the model that we need to explain. As part of our explainability toolbox, we have a class of methods that explain the behavior of a model by querying the model. The key idea is that we can interrogate the model by examining how it behaves in response to controlled variations of input. We treat the model as a black box. We do not consider how the model is coming up with its prediction. We just observe the external output of the model. Then we use what we observe to construct an explanation. We can think of this as some form of transfer learning. We are transferring the knowledge that a complex model has into a simpler explanation representing what the model is doing, not necessarily how the model is doing it. although the approximate explanation is not an exact match of what the model is doing, it is close enough to be useful in understanding the model's logic. And because these explanations are generated from the model, these explanations are referred to as post-hoc. To summarize the explainability options we reviewed, we have intrinsic explanations that assume access to the model and the structure of the model is the explanation. We have post-hoc explanations that assume the ability to query the model. We have global explanations that explain the whole logic of the model and the reasoning behind all possible outcomes. We also have local explanations that explain the model characteristics and the impact of input features for a specific prediction. We have model-specific explanations exclusive to the classifier used and derive their explanation by using the internal model representation or learning process. We have model-agnostic explanations that approximate the behavior of the underlying model to generate end-user explanations that are independent of the internal logic used to generate the prediction.